This is our Adversarial Conway engine in action. The idea is simple and straightforward. Two individual patterns of Conway's famous Game of Life compete on a shared space, trying to grab as many cells as possible, even stealing them from one another, to score points. Notice the statistics under each pattern, or glyph as we call them in this particular context. These give you an idea of the strengths and weaknesses of the opposing glyphs. For example, iteration is the number of steps this pattern runs on its square according to the standard Conway rules, while min and max count the number of alive cells. You may have noticed the yellow dot that keeps jumping around on the glyph square. This is the peak cell, and in today's video I would like to show you the meaning and importance of it. It's probably best to move into the third dimension to better explain what I mean. This here might look complicated, but it's actually quite simple. I'm essentially just stacking each step of the pattern's evolution on top of the previous one. It looks beautiful, doesn't it? Anyway, we are almost there to understand what the peak metric means. Let me reload the same pattern, but this time we don't just stack the pattern's step configurations. Instead, for every step of our glyph's evolution, we look at the 16 by 16 individual cells it's made of. For every step we determine if a cell is dead or alive. If it is alive, we add a block on top of this cell. Hence, we will count how many of the steps all the individual cells have been alive or not. This, in essence, gives us a heat map of which cells are alive the most. Now, peak is just the highest cell here. Peak count is the metric that tells you which cell has been alive the most during the glyph's evolution. I strongly suspect that this is one of those moments where a picture really says more than 1,000 words, isn't it? So what does peak count tell us? When I set up this entire competitive Conway ecosystem, I had a hunch that, apart from a pattern's longevity, its concentration might be a factor that determines whether it wins a duel against another glyph or not. Peak count is a proxy for this concentration. Think about it. A pattern with a high peak count is a pattern that hits a particular cell many times over its evolution. So this means that the glyph evolves in a concentrated way. It does not necessarily use the entire 16 by 16 square at its disposal, but seems to favor certain parts of it. Put another way, a pattern with a low peak count is likely one where its evolutionary steps are spread out more evenly over the 16 by 16 square, so all the individual cells don't accumulate too many of these vertically stacked blocks. But peak count is also telling us something about temporal density, for lack of a better word. A glyph with very sparse configurations does not let its component cells accumulate many blocks on the heat map. Does this help us in understanding if a glyph is strong or weak in a contest? To be honest, we do not know that. We have been conducting a tournament in our battle engine, so to speak, where we pit 32 individual glyphs with varying stats against each other in 1 versus 1 matches to determine the ultimate winner. So far, we have not been able to crack the code yet. It's not entirely clear which of these stats predict a winner. We have even undertaken a first statistical analysis of our tournaments recently to get to the bottom of this. Link in the description. I find this endlessly fascinating. I do not fully understand my own creation. Maybe this mirrors John Conway's own experience when he invented the cellular automaton named after him. Again, simple rules give rise to emergent, complex behavior. Would you like to know how exactly the Adversarial Conway algorithm works? Then leave a comment and like and subscribe. Until next time, if you wish.